Hello, everyone. Thank you for joining us today. My name is Yasmina Greco. I'm with O'Reilly Media, and I will be your host for today's webcast. Today we have Allen Downey presenting Bayesian Statistics Made Simple. Allen is the author of the brand new O'Reilly book, Think Python. He is also the author of the best-selling O'Reilly book, ThinkStats. We're so thrilled to have him with us today to present this webcast for you all. I will turn the program over to Allen in just a moment, but first I'd like to go over some housekeeping things to help you get the most out of today's webcast. You'll want to open the group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for Allen. We find that our audience usually has a lot of good knowledge to share, so we encourage you all to chat freely during the event. However, if you have questions for Allen, please preface them with a capital letter Q so we know that they're for him and we can make sure he sees them for Q&A. You can also open, move, and resize any of the other widgets. If you'd like to tweet from the Twitter widget today, you may need to give it permission to access your account. It will automatically append the event's hashtag to your tweets, so you don't have to. And our hashtag today is StrataConf, all one word. If you have any problems during the event, please take a look at the Help widget. If you continue to have problems, please post it in the chat room, and one of our staff will help you right away. For choppy audio or stalled visuals, please try refreshing your window. And remember, the best thing you can do for a good audio stream is to close any apps that could interfere. People always ask, so we'd like you to know we are recording today's webcast, and we'll have an archive ready usually within 48 hours. And folks, at this time, it is my pleasure to turn the program over to Allen for his presentation. Hello, Allen.
Hi. Great. Thank you very much, Yasmina, and thank you all for tuning in. If you look at my title slide, I'm Allen Downey. I teach at Olin College in Needham, Massachusetts. And if you look, I've got the URL for my slides there. So if you want to download the slides, you can follow along, or you can take a look at them later on. So a lot of what I'm going to be presenting today is based on material from ThinkStats, which is available from O'Reilly. You can also download it from ThinkStatscom. And part of what I'm going to be talking about today is from a new book that I'm working on now called Think Bayes, Bayesian Statistics Made Simple. The current draft of that is available from thinkbayes.com. This is a work in progress, so if you get a chance to look at that and you have comments or suggestions, please let me know. That's very helpful to me as I'm finishing the book. A couple of thoughts. There are some prerequisites for this talk, and one of them, I'm going to be showing a lot of code examples in Python. If you know Python, that's great. If you don't, they are probably still understandable, but I think it'll be a little bit easier for you if you're familiar with that. And then the other is I'm going to assume that you know a little bit about probability, but not very much. In fact, I'm going to get started by explaining my notation here for conditional probability. I'll write P of A for the probability that some event, which I'm just going to record, denote by A, occurs. So P of A bar B is the probability that A occurs given that B has occurred or that we know that B has occurred. So that's the conditional probability. And then the last piece that we need is P of A and B. That's the probability that both events occur. So A occurs and B occurs. And you can compute that probability by computing P of A, the probability of A, and the conditional probability of B given that A has occurred. It turns out if you know that, you know everything you need to know in order to derive Bayes' theorem. So I'm going to do that in just a couple of steps. First, just by the definition of conjoint probability, we know that the probability of A and B is equal to the probability of B and A. So we can write the two expressions on the right-hand side there, which are probability of A and the conditional probability of B given A. That has to be equal to the probability of B times the conditional probability of A given B. That's equation 2 on the slide. And now all we have to do is divide both sides of the equation by the probability of B, and the result is Bayes' theorem, which I have here conveniently in neon form. So that's probably worth memorizing if you're going to learn one thing from this talk. You want that. There are two ways that you might think about what Bayes' theorem is doing. One way is to think about it as an algorithm to get from one conditional probability to another. So if for some reason you know the probability of B given A, and what you really want is the probability of A given B, you can get from one to the other, provided that you know the other two terms. So this is useful if it turns out that the three terms on the right-hand side are easier than the one term on the left-hand side, then you can use this as an algorithm. It's like a divide and conquer strategy. The other interpretation of Bayes' theorem is called the diachronic interpretation. Diachronic means through time, and the notion here is that you have a hypothesis, and before you see a new body of data, you have some prior probability for that hypothesis, which is P of H. That's the probability of the hypothesis before you see the data. When new data becomes available, if it's relevant, you should update your probability for that hypothesis in order to get what's called the posterior probability, probability of H given D. So that's the diachronic interpretation of Bayes' theorem, and that's most of what I'm going to be talking about today. This is getting a little bit abstract, so I want to show one example. We're going to do the same problem here twice. This is called the cookie problem. I actually got this from a Wikipedia page. The premise is there are two bowls of cookies. Bowl number 1 has 10 chocolate cookies and 30 vanilla cookies. Bowl number 2 has 20 of each. So if you, or Fred, picks a bowl totally at random and then picks a cookie at random, and the cookie turns out to be a vanilla cookie, the question is, what's the probability that the cookie was chosen from bowl number 1? So I'm going to do this two ways. I'm going to do it using Bayes' theorem, and then I'm going to show you a computational version of the same thing. And that computational tool is what I'm going to use for the rest of the talk. So first we have to define what we mean by the hypothesis and the data. The hypothesis in this case is that the cookie came from bowl 1, and the data is that the cookie is a vanilla cookie. So again, given the prior probability for the hypothesis, we want to find the posterior for the hypothesis. We're going to do that by applying Bayes' theorem. So the thing on the left, again, is the probability of the hypothesis given the data. The three terms on the right-hand side are P of H, that's the prior, P of D given H, and that's the conditional likelihood of the data, and then the denominator is P of D, which is the total likelihood of the data. So in this case, we can fill in some numbers. We were told that we chose the bowl totally at random, so we can interpret that as meaning that the prior probability for bowl 1 is 1/2, and so the probability for bowl 2 is also 1/2. The likelihood now of the data is the probability of selecting a vanilla cookie if this hypothesis is true. So if I selected from bowl number 1, then the chance of getting a vanilla cookie is 3/4. And then the denominator is the total likelihood of getting a vanilla cookie from either bowl. So if we add up all the cookies in both bowls, the denominator is 5/8. And if we take those three terms and plug them into Bayes' theorem, we get the answer at the top of the screen, which is 3/5. So if you were doing this by hand, this is how you would do it. What I want to show you next is a set of computational tools that I use for solving problems like this. The first tool is a simple class called PMF. PMF stands for Probability Mass Function. And it's a data structure in Python that I'm going to use as a map from possible values that might occur to the probabilities of those values. The fact that this is a map might give you a hint that this thing is implemented using a Python dictionary, and in fact, that's what it is. So here's what it looks like. If you want to use this library, you would import PMF from ThinkBayes, which is a module that I provide along with the book that I'm working on. To make an empty PMF, you just create a new object, and then the example on the slide shows how you would denote the 6 possible outcomes of rolling a 6-sided die, and the probability of each one of them is 1 out of 6. So that's just a small example of how to use this library. So to do this computationally, I'll do this in 3 steps. First, I'm going to use that PMF object that I just showed you to build a PMF that represents the map from each hypothesis to its prior probability. And then I need to compute the likelihood of each hypothesis. And I'm going to take those prior probabilities and multiply them by the likelihoods. And then the last thing is to normalize the PMF. And what I mean is to add up the total likelihood for all the hypotheses and divide through. So here's what that looks like in code. The first step is just to create the PMF object and create the two hypotheses. In this case, I'm just using Python strings to represent the two hypotheses. And each one of them has a prior probability of 0.5. And the set method just associates a particular probability with a particular hypothesis. In order to update the priors and compute the posteriors, I need to know the likelihood of seeing the data under each hypothesis. So the first line there in blue is the probability of a vanilla cookie given that it was taken from bowl 1. And we know that the likelihood of that is 30 cookies out of the 40. And similarly, the probability of getting a vanilla cookie from bowl 2 is 20 out of 40. So the likelihoods are easy to compute, and then all we have to do is use the mult method to multiply the probability that's associated with bowl 1 by 0.75 and multiply the probability associated with bowl 2 by 0.5. The last step is to invoke the normalize method, which adds up the total probability of the data and then divides through all the probabilities in the PMF. So the result is a normalized PMF where all the probabilities add up to 1. And if we print the probability for bowl 1, the answer is 0.6, which is the same as the 3/5 that we got when we did it arithmetically. So here's where we are so far. We derived Bayes' theorem, and then I used the cookie problem as an opportunity to introduce the PMS class. Step 2 of this talk is what I'll call the dice problem. So let me introduce that. The premise is that I have a box of dice that contains a 4-sided die, 6-sided, 8-sided, 12-sided, and a 20-sided die. And if you've ever played Dungeons & Dragons, you know that it is actually true that I have a box of dice that contains those different dice in it. So suppose I select one of the dice from the box totally at random, roll it, and I get a 6. What I'd like to know now is what's the posterior probability that the die that I rolled is the 4-sided, the 6, 8, or 12-sided die? To answer this question, I'm going to introduce another data structure. This is called a suite, and it is a parent class. It's a child class of PMF. It inherits from PMF. What a suite is a set of hypotheses that are mutually exclusive and collectively exhaustive, which is just a long way of saying that at least one of the hypotheses must be true. So in this case, I'm going to have one hypothesis for each of the dice, and I know that it's exactly one of the dice that I selected when I chose one. So here's what the code looks like. As I said, suite extends PMF, so I'm going to define a new class that inherits from the existing class. And I need to provide two methods. I need to provide an init method. In this case, it takes the list of hypotheses, and it creates an initial distribution where the probability of each hypothesis is 1. And then when it normalizes it, it's going to divide through. So it will be 1 over n if there are n hypotheses. The second method I need is the update method. And this takes some representation of the data as an argument. And what it does is it loops through all the possible values in the suite. And each value in the suite is a hypothesis. It's going to compute the likelihood for each hypothesis by calling the likelihood function. And then it's going to multiply the probability associated with that hypothesis by the likelihood that we just computed, and then renormalize the distribution. Now, one thing that I haven't told you yet is what the likelihood function is. And here's the idea. The likelihood is an abstract method. So update is the parent class here, and I'm going to create new child classes that provide the likelihood function. The reason this is a useful thing is that every Bayesian update is pretty much going to look the same. So the update function doesn't have to change. For any new problem that comes along, all I have to do is fill in the likelihood function. So in this case, the question is, if the outcome is a 6, so I chose a die, I don't know which die it is, I roll it and I get a 6. Well, I can answer the question, what's the likelihood of getting that outcome if, in fact, it is a 6-sided die? And in that case, the chance of getting a 6 on a 6-sided die is 1 in 6, no mystery there. If I know that it's a 10-sided die, then the chance of getting a 6 is 1 in 10. If it's a 20-sided die, it's 1 in 20. So that's all very straightforward. The only slightly tricky one is, what's the likelihood of getting a 6 on a 4-sided die? Well, that's not possible, so the likelihood is 0. So in general, I can write a function that's going to compute what's the likelihood of getting some particular outcome n on a die that has m sides on it. And here's what that looks like in code. I'm going to create a new class called dice that extends suite and that provides the likelihood function. The likelihood function is going to take a hypothesis and some data. In this case, the hypothesis represents the number of sides on the die, and the data is the outcome. So if my hypothesis is less than the data, then that means that I rolled a value that's higher than the number of sides on the die. That's not possible, so I have to return 0. The alternative is if I rolled a valid number, then the chance of getting it is 1 divided by the number of sides on the die. So that's it. For this problem, once I've got the likelihood function, I can pretty much turn off my brain, because everything from here on in is pretty much mechanical. I'm going to create a new suite that has a list of hypotheses with one hypothesis for each possible die. Again, 4-sided, 6-sided, 8, 12, and 20. I'm going to call the update function, and what I pass to the update function is the outcome of rolling a die, which in this case is 6. The update function automatically calls that likelihood function that we just wrote, and then it normalizes the distribution. So when I'm done, I can just invoke suite.print, and that'll give me the list of hypotheses and the posterior probability associated with each one. So the posterior probability for the 4-sided die is 0, and that makes sense because I saw an outcome, 6, that couldn't possibly come from a 4-sided die. So I've ruled out the hypothesis that it's a 4-sided die. The 6-sided die is still quite likely, about 40%, but the 8-sided die, the 12-sided, even the 20-sided die have not been ruled out by the data that I've seen so far. It's just one roll of the die. The next step is very simple. This is if I roll the die a few more times, let's say that I get 4, 8, 7, 7, 2, 6, whatever the data are, I can just do successive updates of the same suite. And each update is going to take account of the new data and produce a new posterior distribution. So after I've seen this sequence of rolls, I can print the resulting data again. This posterior distribution shows that at this point, I've ruled out the 4-sided die. I've ruled out the 6-sided die. And in fact, the likelihood or the posterior probability for the 8-sided die at this point is pretty high. It's almost 95%. The 12 and 20-sided die have not been ruled out as a hypothesis. It's still possible. It's just unlikely that after 7 or 8 rolls, whatever it was, it's unlikely that I would never see a value higher than 8 unless it was an 8-sided die. So that's the end of the second example, just to summarize where we are so far. We started with Bayes' theorem. We did the cookie problem and introduced the PMF class. And then I introduced the dice problem. We have this, and that introduces the suite class, which provides a framework for solving these kinds of Bayesian problems that come up over and over. All you have to do for a new problem is plug in what the new likelihood function is. Everything else is the same. Okay, we're going to do one more problem, and I'm going to use this as an example of both estimation and Bayesian hypothesis testing. So here's the problem. This comes from David Mackay's book, which is called Information Theory, Inference, and Learning Algorithms. He presented this problem based on a quote from the Guardian newspaper. This is when the first euro coins were being introduced in Europe, and in particular the Belgian euro coin drew attention. One researcher spun the coin on edge 250 times, and it came up heads 140 times and tails 110 times. They consulted a statistician who said, it looks very suspicious to me. If the coin were unbiased, the chance of getting a result as extreme as that would be less than 7%. So David Mackay picked this problem in his book because it turns out that there's an interesting way that we can ask the question here, which is, do these data, seeing 140 heads out of 250 spins, give evidence that the coin is biased rather than fair? And as I said, I'm going to use this first as an estimation problem and then to introduce the idea of Bayesian hypothesis testing. So I'm going to throw in one small bit of notation, which is I'm going to assume that any given coin, when it's spun on edge until it falls over one way or the other, has some probability of landing heads up. And I'm just going to call that probability X. I'm going to avoid calling it P just because that gets confusing. So I mentioned estimation. What I mean by that is that we're going to use the data in order to try to figure out for each possible value of X, what's the probability of that value. And then the second step is going to be to answer the question the way David Mackay posed it, which is, what's the probability that the coin is fair? Again, we're going to use the sweet template, so we don't have to write the update function over and over. We just have to figure out the likelihood function. And here's what that looks like. Again, I'm going to create a new class called Euro. It's going to extend sweet, so it inherits the update function, and I have to provide the likelihood function. And the signature for the likelihood function is the same every time. It takes a hypothesis and a body of data. But what you can do each time you set up one of these problems, you get to choose what is the representation of the hypothesis and what's the representation of the data. In this case, I chose for the hypothesis a number from 1 to 100 that represents the probability that the coin will land heads up. And for the data, it's a simple string that's either H for heads or T for tails. So if we know that the probability of landing heads up is X, then the probability of heads is X, and the probability of tails is 1 minus X. So this is a case where computing the likelihood function is really very simple. The next step is to choose the prior distribution. And so the question here is, if I showed you a coin that you had never seen before and asked you, what do you think is the probability that this coin will land heads up if I spin it on edge until it falls over? And you might think about that a bit, take into account what you know about coins and all that. You might have some background knowledge that you would use to choose an appropriate prior. I want to come back to that in a couple of minutes. I'm going to start with something very simple, and then we'll look at some alternatives. So one simple choice is just to say that the prior distribution for X is uniform between 0 and 100%. And I'm saying, in effect, that if I don't know anything about a coin, I'm going to assume that X could be anything. Here's what that looks like in code. I'm just going to create a new suite called by instantiating the Euro class, and I'm going to pass as a parameter the range from 0 to 101. I have to go to 101 because in Python the range is the endpoint minus 1. Here's what that looks like graphically. So the horizontal axis here shows all the different values of X. From 0 on the left-hand side, that means that this coin has no chance of landing heads up, to 100% on the right-hand side, and that means that it always lands head up. 50-50 in the middle would be an unbiased coin. And I'm starting with the prior belief that any value for X is equally likely. So let's suppose that we just spin the coin once and it comes up heads. I can take that suite that I just instantiated and call the update function with one value of H. And now we can compute the posterior distribution. Before I show it to you, I want you to think for just a second about what it's going to look like. And one way to think about this is, given that we just spun the coin and got heads, what's the probability that X is 0? So you can think about that, and now I'll show you what the posterior distribution looks like. As you might expect, the posterior probability for X equals 0 is 0. Because a coin that has X equals 0 has no chance of landing heads up. And since I just saw a heads, it can't be that coin. On the other hand, a coin that always lands head up has a very high likelihood, and so it gets a very high posterior probability. And a value in the middle, like x equals 50%, has a likelihood of 50%, and so it ends up with a middling posterior probability. Let's do a couple more steps. We'll work our way up to the entire body of data. Suppose we spin the coin again and get heads again. So now we've seen 2 consecutive heads. Again, I want you to think a little bit about what the posterior distribution looks like before I show it to you. Now at the low end, on the left side, it still has to be 0. But what happens to the right-hand side? The answer is that for high values of x, the likelihood is still high, and so the posterior probability is still high. On the low end, if x were, say, 20%, that means that there's only a 1 in 5 chance of getting heads, and so the fact that I've seen 2 consecutive heads is unlikely. If you think about the math of what's going on here, this is in fact a parabola, but since we're doing this computationally, I won't get too hung up on the analysis of it. I'll do one last extension of this. Let's say that we spin the same coin one more time. This time we get heads. So we've seen tails. This time we've seen 2 heads and 1 tails. Now what does the posterior distribution look like? And now it should occur to you that in the same way that we ruled out x equals 0, now because we've seen tails, we've also ruled out x equals 100. And so the posterior distribution looks like this. So 0 is ruled out, 100 is ruled out, and the most likely value, somewhere close to the middle, is 66%, which makes sense because I've now seen 2 heads and 1 tails. So the observed probability is 66%, and that is in fact the most likely value in the posterior distribution. As we add more data, the posterior distribution is going to get narrower and narrower around a more specific value. So if I've seen 7 heads and 3 tails, the posterior distribution looks like this. It's now centered around 70%, or I should say the most likely value is 70%, and a little bit narrower than what we saw before. And finally, we can use the actual data that we were given in the problem, which is 140 instances of H and 110 instances of T. We can write the same loop to do the update, and the posterior distribution looks like this. So having seen all that data, we now have a pretty narrow posterior distribution. Pretty much anything less than 40% or higher than about 70% has been almost ruled out. Those probabilities are not actually 0. They're just very close to 0. And for practical purposes, we could pretty much round down. But the question now is, okay, so I've got a posterior distribution of x, but how do I use that to answer the question that I started with, which is this thing a fair coin? So this is one tempting option that turns out not to be right. If we want to know whether the coin is fair, we could ask, well, what's the posterior probability that x is 50%? We can compute that. The answer turns out to be 0.021, but that's kind of a meaningless number, in particular because I chose my prior distribution arbitrarily and I discretized it arbitrarily. I could have chopped it up into more or fewer steps, and if I had, then that posterior probability would be very different. So in fact, taking the posterior and then asking for the probability of one particular value isn't the right question to ask in this case. There are some other questions we can ask. So one of them that I mentioned before is, what's the most likely value? If you had to make a single guess for what the probability is for that particular coin, you could loop through all the hypotheses and all of their probabilities in the posterior distribution and just pick the one with the highest posterior probability. And in this case, the value of x that you would guess is 56%. A very similar option would be to compute the mean of the posterior distribution. I just wanted to show you the code for how to do that because it gives a nice example of how you can work with a posterior distribution in order to generate these different summary statistics. So the mean value turns out to be 55.95, which is very close to the most likely value, 56. If you studied classical statistics, you're familiar with confidence intervals. So the natural next question to ask is, what is the range in this posterior distribution that contains 90% of the probability? And you can find that by computing the 5th and 95th percentiles of the posterior distribution. So here's some code that computes, that takes the PMF, which is the posterior distribution, and computes a percentile. The 5th percentile turns out to be 51, and the 95th percentile is 61. So we could make a confidence interval between 51 and 61. And the question is, can we now summarize that by saying there's a 90% chance that X falls between 51 and 61%? And the answer, if you are thinking in terms of frequentist statistics, is emphatically no. In fact, we spend a lot of time in statistics class understanding what confidence intervals mean. And the interpretation that we just gave is explicitly forbidden in frequentist statistics. In Bayesian statistics, it is perfectly acceptable to think of X, which is the probability of landing heads. You can think of that as being a random variable. And in that case, we would call that range, 51 to 61, a credible interval. And you would meaningfully say that there is a 90% probability that X falls in that range. So that's one nice thing about the Bayesian approach, is that we can make meaningful probability statements using the posterior distribution. There's one drawback of this approach to the problem, though, which is that the prior distribution that we chose was a subjective choice. I chose a uniform distribution arbitrarily, but that uniform distribution is effectively saying that if you show me a coin, I think it's just as likely that that coin is a fair coin with X equals 50%, as it would be for that coin to be a completely biased coin with only a 1% chance of landing heads. And if you think about the physics of spinning a coin on edge, and if the coin is not absurdly misformed, it just doesn't seem like that's the right prior distribution. So an alternative would be to try to capture the background knowledge that we have about coins by choosing a more intelligent prior distribution. In this case, something that's triangle-shaped probably makes sense. So I picked one, and this again, it's somewhat arbitrary, but it at least has some logic to it. That says, I think that most coins are pretty close to fair. Usually the value for X is pretty close to 50%. There might be some really extreme coins where it's 20% or 80%, but I'm going to rule out the possibility of, it can't be 0, it can't be 100%. So that's what my prior distribution looks like. Again, before I show you what the posterior distribution looks like for this new prior, I want you to think about it for just a second, and then I'll show it to you. So here it is. The blue line is the posterior distribution that's based on the uniform prior, and the green line is the posterior distribution that's based on the triangle prior. And what you see is that they are so similar to each other that you almost can't see the overlap. This is a process that's sometimes called swamping the prior. And the notion is, if you have different people who start with different subjective beliefs, so they start out with different priors, eventually if you show them enough data, they will tend to converge. They may not ever completely agree, and in fact mathematically they won't ever completely agree, but they might get close enough that for practical purposes they would get along just fine. And that'll be true as long as you start with a reasonable prior, and as long as you do a Bayesian update. What I mean by a reasonable prior is that you should avoid giving a probability of 0 as a prior probability for any hypothesis. The problem is that if you give a hypothesis a prior probability of 0, there is no amount of data that will ever change your opinion about that. So as a general heuristic, if you are willing, if you think the hypothesis is extremely unlikely, you can give it a prior that is arbitrarily low. That's fine. As long as it's anything but 0, there can, at least in theory, be enough evidence to eventually change your mind. So let me summarize where we are so far. I've talked about Bayesian estimation, and the approach to estimation that I'm proposing is that you form a suite of hypotheses, which I'll use the notation H sub I. So each H sub I is one hypothesis about the parameter that you're trying to estimate. Then you choose a prior distribution, which is the probability for each H sub I before you see the data. Compute the likelihood for each hypothesis. So what would be the chance of seeing the data that I saw if h sub I is true. And then once you've figured out what the likelihood function looks like, you can pretty much turn off your brain. Computing the posterior distribution is going to be the same for every Bayesian problem that you do. So that's the end of estimation. The problem is that we haven't really answered the question that we started with. What Mackay asked was, do these data give evidence that the coin is biased rather than fair? And to answer that question, I have to start with, what does it mean to say that data give evidence for a hypothesis or against a hypothesis? Here's the Bayesian way of thinking about that. Some data set that you observe, D, is evidence in favor of some hypothesis, H, if the probability of H after you saw the data is higher than your prior probability before you saw the data. And that will be true exactly if the probability of the data, if the likelihood of the data is higher given H than given not H, then you can think of that data as being evidence in favor of H. Instead of comparing those two values, it's very common to write them as a ratio, which is the likelihood of the data given H divided by the likelihood of the data given not H. And if that ratio is greater than 1, then we would consider D to be evidence in favor of H. That ratio is sometimes called a likelihood ratio, or it's called the Bayes factor, and it's a measure of the strength of the evidence. So if the Bayes factor is exactly 1, then we would say that D doesn't give you any evidence one way or the other. If that ratio, the Bayes factor, is much greater than 1, we would say that it gives strong evidence in favor of H. And if it's much less than 1, we would say it gives strong evidence against H. So let's see how we can apply that to the Euro problem. We'll define two hypotheses. So F is the hypothesis that the coin is fair. B is the hypothesis that the coin is biased. If we want to compute what's the probability of the data given that the coin is fair, that's easy to do. If the coin is fair, then we know that X is exactly 50%. And so we can compute the probability of getting 140 heads out of 250 spins, given that X is 50%. But in order to compute a likelihood ratio, we have to get both of these terms. And the other term is the likelihood of the data given B. The problem is that we haven't really specified what B is. We've said that the coin is biased, but we haven't been clear about what that means. So one option which is very tempting is to look at the data and say, okay, well, we got 140 heads out of 250 spins. So my hypothesis B is that X is 140 out of 250. Now, if that move bothers you, then your intuition is pretty good, because it does seem like it's a bit of a cheat to look at the data in order to choose your hypothesis, and then use the data to update the probability of that hypothesis. And in fact, you're only allowed to use each data point once. So we need some ground rules for how we're going to compare these two hypotheses. Rule number 1 is you have to choose your hypothesis before you see the data. So you're not allowed to do what we just did. The other is, if you want to define a suite of hypotheses, so for example, if you say, I think the coin is biased, and that means that X might take on a range of different values other than 50%, you can have a hypothesis like that. But if you do that, then the way we're going to compute the likelihood is by averaging over all the hypotheses in your suite. I like to think of this as analogous to playing roulette, which is you can put all your money on one number in roulette, or you can spread your bet out over a lot of different numbers. And either way, the payoff that you get is going to be the weighted average of the outcome and the wager that you made. And that's exactly what the code looks like. If you give me a suite that represents your prior belief about X, and then I evaluate a body of data, what I can do is loop through all the hypotheses in your suite. And for each suite, I'm going to compute the likelihood of the data under that hypothesis, and then add up the weighted average of those likelihoods, where the weights are proportional to the prior probabilities in your suite. That was kind of a lot to process, so let me show the example, and maybe that'll become a little bit clearer. So again, I'm going to define F is the hypothesis that x is exactly 50%. And B is the hypothesis that x is anything except 50%, but it's equally likely to be any value between 0 and 100. So now I can build a suite that represents the fair hypothesis. It only has one value in it, 50%, and that value has probability 1. And I can build a second suite that represents the biased hypothesis. So here, I'm going to loop through all the values from 0 to 100, and I'm going to give equal prior probability to every value except 50. 50 is ruled out. Turns out it doesn't really matter that I excluded 50. I did it for clarity, but it doesn't make any difference in the outcome. And then I can compute the Bayes factor by using the average likelihood function that I showed you a minute ago to compute the average likelihood for the fair hypothesis, the average likelihood for the biased hypothesis, and then the likelihood ratio, which is the Bayes factor. It turns out in both cases that the likelihood of getting any particular outcome is usually quite low. In this case, it works out to numbers that are on the order of 10 to the minus 76. So these are very small numbers, but in some sense that's irrelevant. I don't really care what the likelihood is for a particular outcome. What I care about is the likelihood ratio. And in this case, the likelihood ratio works out to be about 0.5, and that means that this data set is evidence against the hypothesis that this coin is biased. So that's the end of that example. I just want to summarize what we've done so far. We started out with Bayes' theorem, did the cookie problem. I introduced the PMF class and the suite class, and that gave us a framework for solving lots of different Bayesian problems. And so for each problem, we really only have to figure out what's the likelihood function, and then everything else follows from there. And we did one example of Bayesian estimation and one example of Bayesian hypothesis testing. If you want to read more about this, as I said, most of the examples that I've just talked about are in Think Bayes, which is this book that I'm working on now. So if you get a chance to look at that and you have any comments or suggestions, I welcome that. There are a couple of books that I recommend. I got the Euro problem from a book by David Mackay that I think is very good. This is the place where I learned about Bayesian statistics, so I have a fond memory of it. It's called Information Theory, Inference, and Learning Algorithms. And then there are two other books there that are very well regarded as an introduction to Bayesian statistics. Both of them tend to use continuous mathematics more than the examples that I've used here that are based on discrete mathematics. A couple of other books that you might like to read. I mentioned ThinkStats, which is my basic introduction to exploratory data analysis. If you're not comfortable with Python, you might enjoy ThinkPython, which is an introduction to Python programming for people who have very little or no programming experience. ThinkPython, going along with today's webcast, ThinkPython is on sale over at the O'Reilly shop. So if you want to go check that out after this talk, you can do that. And then Think Complexity is a different book of mine that's on a different topic, but I thought I would mention it. That's all I'll talk about for now, and I can take some questions.
Great. Thank you so much for a fascinating webcast, Alan. And we do, of course, have several questions that have come in. And a quick announcement, folks, if you do have a question for Alan, we are at Q&A. Please open your group chat widget. If you haven't done that already, type it in, send it in so he can answer it while he's with us. Let's see, in the order they came in, first question here, which version of Python does your code use, 2.7 or Python 3?
So I'm using Python 2.7. There's very little that I'm doing that takes advantage of differences between 2.7 and 3. So all of my code could be ported very easily to Python 3, but I'm not currently providing the translation just because it's a little bit difficult for me to maintain different versions.
Thank you. Another question. What are some typical problem areas or domains that Bayes stats are well suited for working with?
Right. So the primary area that people think about when they think about Bayesian statistics are cases where you have a relatively small amount of data and you're trying to squeeze the most possible information out of it. And Bayesian statistics does a nice job in that space because it allows you to take advantage of the background information that you have about the problem and encode that background information in the form of the prior distribution. And then even if you have very small amounts of data, you can do an update and then the result is a posterior distribution. The nice thing about having a posterior distribution is that it's not just a single valued estimate. It's the entire distribution of possible outcomes. The nice thing about that is now if you want to reduce that down to a single estimate, you can. If you want a confidence interval, you can get that. Or what's often the case is that you now want to take that posterior distribution and do some additional analysis on it. So for example, if you know what the cost would be that's associated with a particular error, then you could integrate the posterior distribution over the error function and get a prediction of how much your uncertainty would cost.
Thank you. Another question here from Philip. Philip would like to know if you can talk a little bit more about the normalized function.
The normalized function. So that's actually very simple, and I probably should have just shown the code. The only thing that it does is it adds up all the probabilities that are in the PMF, and then it divides through by that total probability. And so the result will always be a PMF where the total probability is 1. In the context of a Bayesian update, what you're doing when you normalize the PMF, what you're doing is you're adding up all the posterior probabilities, and what that gives you is the denominator of Bayes' theorem. That gives you the total probability of the data. And so when you normalize, you're dividing through by the probability. That's the last step of applying Bayes' theorem.
Thank you. Let's see here. Another question from Christopher. Christopher would like to know, this is regarding the graphs in your presentation, does thinkbayes.py draw the graphs?
Oh, right. No, all the graphs I showed here are from matplotlib, which is a nice package that does almost all of the same plotting that MATLAB does. So it generally makes pretty good figures. I have a very thin library that I call myplot. That's a wrapper that I put around pyplot, but I'm not really doing anything special. So that's mostly just straight matplotlib.
Thank you. A question here from Kojo. If the likelihood ratio is 1, does that mean the data is inconclusive with regard to support/dispute of the hypothesis?
Kind of. I don't think I would say inconclusive. I would almost say irrelevant. So if the Bayes factor is 1, then that means that the data don't tell you anything about the hypothesis one way or the other. So whatever your prior belief was, that's going to be your posterior as well. So it would be as if you wanted to know the probability that a euro coin is biased, and you rolled a die and you got 3. Well, rolling a die has nothing to do with flipping the coin, so the Bayes factor would be 1. In terms of information theory, you would say it contains no information about the hypothesis.
Great. And our final question here, can Bayesian stats reduce test times in web/A/B testing?
Can they reduce test times in A/B testing? They have possibly. It's a little bit of a dangerous thing. So the advantage of Bayesian statistics there is you can use a very small amount of data, and you can quit as soon as you see satisfactory evidence that one of them is better than the other. There's a little bit of a danger there, which is that even if they're the same, there's some probability that you would eventually become convinced that they're different. So you still have to beware of false positives. But yes, in general, a Bayesian approach to that kind of problem would work very nicely.
Great. I'm not seeing any.
That's a good idea. I'm going to do an example of that in the book. So I think this is one of the nice things about doing an early draft of the book is that I get a lot of feedback. And that question is a great example. So I will put that into the book. The other useful piece of information that I got, I had a draft earlier that had an example in it that nobody liked. Everybody was complaining about this example because it was either confusing or wrong, depending on who you talk to. And I'm just glad I got that feedback early because I just pulled that example out of the book and it will never bother anyone again.
Super. Allen, I'm not seeing any additional questions, so with that, we are going to say a very big thank you to you, sir, for presenting this outstanding webcast for us today, for sharing all your knowledge and expertise with us. We'd like to say a thank you to all the attendees who attended today and hope you benefited from it. And I'm just looking through the comments of the chat box, and from what I'm seeing, Ellen, everyone really did enjoy this event, and there was a lot of good discussion going on. So again, we thank you for presenting it. Folks, we'd like to let you know Ellen's book, Think Python, is the O'Reilly Deal of the Day, and what that means for you is you can get it today and save some money as a thank you for attending the webcast. Please visit O'Reilly.com. Look on the right-hand side. You can't miss it. It's right there. And we also pushed out some details and a code for you all in your group chat about that to save you some money. Again, we thank you, Ellen. Thank you, everyone. This will conclude today's webcast. Goodbye, everybody.